So in this today's lecture, we are going to look at the Norton's theorem, another important theorem in electrical engineering, which is used to find the currents on a given load for possibly different values of the load resistor. This course material should be suitable for undergraduate students of electrical engineering in US, India, or anywhere. So what we will do is we will try to put up an example and we will understand from that example. So let me draw a circuit. So I draw a circle. It has a simple two voltage sources, 28 volt and 7 volt. And there is a 4 ohm resistor, 1 ohm resistor, and this is my load resistor. So Norton says that this whole circuit, multiple voltages, sources, and many resistances. I have 2 resistances and 2 voltage sources, but a more complex circuit could have many more sources and a resistor. This whole thing could be replaced by a very simple circuit that consists of a current source and a resistor in parallel with it, and then you can connect your load between these 2 points A and B. And if you have this simple circuit, you can change the value of the load connected between points A and B for different values and keep on calculating the current flowing in this resistor for those different values of RL. This current source will be called the value IN, and this resistor value we'll call it RN. The question is, what are these values of IN and RN? If you have not checked my previous lecture on Thevenin's theorem, I will suggest you to go back and check that as well if you have not seen this. Norton says that this Thevenin's resistor, this resistance, this Norton resistance Rn is same as the Thevenin's resistance, which is found by, how do we find this resistance Rn? To do this, take this circuit, take these points A and B in this circuit, and mentally replace all the voltage sources with a short circuit. Short circuit this, short circuit this. In this circuit, there is no current source, but if there is a current source as well in this complex circuit, replace all those current sources with open circuit. If they have some internal resistance, replace them with their internal resistance. And then once we have done that, in that mode, also remove this RL load resistor away from this picture, and then find out what is the resistor across these points A and B. That will be Rn. Rn is same as Rth that we discussed in Thevenin's theorem. Practically, if you have a circuit like this on your circuit board or somewhere, you could replace this whole voltage sources, remove them and short them. For example, if you have like a power supply, just turn off the power supplies and short these 2 terminals. And then use a multimeter to measure the resistance between these 2 points. That is what practically Rn is. So let's calculate the Rn in this circuit. So accordingly, what we have, the circuit is like this, 4 ohm here. This is shorted, so it looks like this. This is the point in between which we need to find the resistance. And I have shorted this 7 volt, so it looks like this. This is 4 ohm, this is 1 ohm. This practically is nothing but 2 resistors in parallel. If you want, you can make it look like this. A and B, this is 4 ohm, this is 1 ohm. And the equivalent resistance of these 2 parallel resistors is 4 into 1 divided by 4 plus 1 or 4 divided by 5. So we have calculated Rn equal to 4 by 5 ohm. Norton says the next important thing, how do you calculate In? For this he gives the tip that remove this resistance RL from this picture and then connect an ammeter on this or short this and find the current flowing in that short. So this is 4 ohm, this is 1 ohm, this is 28 volt, and I have shorted this terminal. This is 7 volt. We need to find out the current flowing in this resistor, and we will be using simple Kirchhoff laws using these two loops. Let us say the current flowing in this one is I1 and current flowing from this due to this branch is I2. I am trying to mentally imagine that this 8 volt battery will try to send a current in this direction, and this one will also try to send a current in this direction. The currents come here, meet together and become I1 plus I2 in this branch. Now we have two loops. One is this loop, another is this loop. In this loop, this 28 volt is trying to make the current flow through this. So we have the resistance 28 is equal to 4 into I1. This gives I1 equal to 7 amp. This is our first value of R. In this loop, we have the 7 volt is giving a IR drop of 1 into I2. I2 is 7 ampere. So the Norton's current, this current is I1 plus I2 is equal to 14 amp. You add these two, you get 14 amps of current. And this is our IN. So what does Norton say? This IN is 14 amp. Now how does this help in finding the current in this load resistor? This is the next thing we are going to calculate in this law. Now that we have found this, all we have to do is we have replaced this whole circuit with a circuit that has a current source of 14 amp, a resistor of 4 by 5 amp, 5 ohm, and then this is the load resistor RL. We need to find for 2 ohm. And in this circuit, this 14 ampere current starts flowing in this circuit and is distributed in this I1 in these two branches, one here, one here. The path that has lower resistor will have more current. The path that has higher resistance we have lower current. It's because the voltage, let's say current is I1 here and this is I2 here. If this is I1, this is going to be 14, this is I2, then this is going to be 14 minus I2. And the voltage across this and across this is same. So we have 4 by 5 into 14 minus I2 is equal to 2 into I2. This is simple. Voltage is same across this point, or if you measure voltage across this point. 5 goes on this side, so 10 I2 plus 4 I2, 14 I2 is equal to 4 into 14. 14 cancels. We have I2 is equal to 4 amp. So for this 2 ohm load, we will can calculate the I current as 4 ampere, and then ampere will flow into this. Now we can keep on changing this resistor Rn for different values, and we can keep finding this problem. So this is how the Norton's theorem does. Essentially, the results that are obtained by the Norton theorem and the Thevenin's theorem, they are both are same. Both of them try to find out the current in the load resistors for different values of loads, but one method could be easier in different problem situations than the other, and that's why we need to know both these theorems. Let's take a look at another problem which involves the voltage source as well as the current source. In the meantime, you can write down some comments in this comment section, and I also should have a link to a website where you can find more practice problems and multiple choice problems to enhance your understanding. Sean, keep away. So in this problem, we need to find out the Norton's current and the Norton's resistor. So we can replace this whole circuit using a circuit of like this. IN
G
and this is the resistor Rn. This will be point A and this is point B. So let us try to find out the Rn first, the easier stuff. How do we find Rn? We can find Rn. Mentally remove this load resistor. We are not showing any load resistor here. Mentally it's removed. And all the voltage sources are replaced by short circuit, so this becomes like this. And all the current sources are opened up. We get a circuit like this is 10 ohm, this is 40 ohm, this is 4 ohm, this is point A, this is point B. And we are looking from this side and trying to find out the equivalent resistance of this circuit. So this 10 ohm and 40 ohm, they are in parallel. You rotate this one, so this will start looking like a parallel resistor. And the equivalent resistance of these two resistors will be 10 into 40 divided by 10 plus 40. And this will become 400 divided by 50 or 8 ohm. 8 ohm and 4 ohm, they become in series. So the equivalent resistance is equal to 4 plus 8 is equal to 12 ohm. And this is our Norton's resistance resistor Rn. So we have found the first part, Rn is equal to 12 ohm. Let's try to find out IN. And once we have done that, our Norton's equivalent circuit is ready. We can start calculating the load resistance for different values of load resistance. So how do we find IN? For IN, we need to mentally short the points A and B. So we draw this circuit again. This is 10 ohm. This is 10 volt. $40 ohm. This one is 2 ampere. $4 ohm, and then this is shorted. We need to find out the current flowing here through this 4 ohm. We are interested in the current, so it does not matter how we solve. One way to solve is to use Kirchhoff voltage law, and we will have 1, 2, 3 loops. The problem is there are 3 complicated equations. You can pause this video and try to solve for this current and check back the simpler method. So what I am going to do is, I am trying a simpler trick for this particular problem. Let us assume that the voltage on this node is Vx, and look at the Kirchhoff current law for this particular node. The sum of all the currents, let us say this voltage is a high voltage, and let us say the currents are flowing in this direction, then the sum of these currents should be 0 on this node. So the current flowing in this node is going to be Vx minus 10 divided by 10. The current flowing in this, let us say this voltage is 0. Then Vx, the voltage across this is going to be Vx minus 10, that will be equal to Vx minus 10 divided by 10. This is 10 ohm. And the voltage flowing in this resistor is going to be Vx divided by 40. The voltage flowing in this one is given as 2 ampere. And finally the voltage flowing in this resistor, let us say it has this direction, and that will be equal to Vx upon 4. All this will be equal to 0 by Kirchhoff's current law. What it means is that, let us multiply this whole equation by 40. This is 4 into Vx minus 10 plus Vx plus 80 plus 10 into Vx is equal to 0. This is our equation. Let us simplify that a little bit. 4Vx plus Vx is 5Vx, 5 or plus 10, 15Vx, plus 80 minus 4 into 10, 40. This is 40 is equal to 0. That means Vx is going to be minus 40 divided by 15. If you divide it by 5, it is minus 8 divided by 3. What does it mean? That this voltage Vx is at a negative voltage, and that negative voltage is minus 8 by 3. So minus 8 by 3 voltage is here, 0 volt is here. That means the current flowing in this resistor in this direction, I in this resistor is going to be this voltage minus 8 by 3 divided by 4, or minus 2 by 3 amp. What it tells is that the direction of this current is not in this direction, is not flowing in this direction, it is in the opposite direction. And that therefore the Thevenin's IN is in this direction. And that's how the value of 2 by 3 amp. Now with the current is given and the resistance is given, basically the current will flow like this and it will go in the resistors in this way. Now the current is given, the Norton current is given, resistor network is given. You can find the load current for different values of this load resistor. So this is how we solve the problem using Norton's theorem. We will do one more problem and then you can leave. One more thing. Let us, before we do complete that, let us also try to solve this problem for Thevenin's, using Thevenin's theorem, and make sure that the result that we obtain using the Thevenin's theorem and the Norton theorem, they are the same. What does the Thevenin's theorem say? The Thevenin's theorem says that this circuit can be replaced by a voltage source and a current source and a resistor in series A and B, such that this is RTH. RTH, this resistor is calculated exactly as the same way, and this one will have a value of 12 ohm. But VTH is different. VTH is obtained by open circuiting this thing and calculating the voltage across A and B. So since this 4 ohm, this is open circuited, there is no current flowing in this resistor, so there is no IR drop. So this voltage between A and B is the same as voltage between this and this. So our circuit to calculate is 10 ohm, this is 10 volt, this is 40 ohm, and then this is 2 ampere, and we need to find out the voltage between these 2 points. This is 10 volt. How do we do that? We can again apply the Kirchhoff voltage law. Let us say this is VA and let us say this is at 0 volt. And we use again the Kirchhoff's law. Direction of 2 ampere is given to be in this direction. So VA minus 10 volt divided by this resistor 10 plus VA upon 40 plus 2 ampere is equal to 0. Multiply whole equation by 40. 4 into VA minus 10 plus VA plus 80 is equal to 0. Let us simplify it a little bit. 4 VA plus VA is 5 VA. Minus 40 plus 80 is plus 40. So VA is equal to minus 8 volt. Now the Thevenin voltage is minus 8 volt. That means the actual polarity is reverse to what we had seen. And that is how you see that the current is flowing in this direction here. So this is what we could do using the Thevenin's theorem. And one of the reasons I did was, this is the next trick, that this Thevenin's equivalent resistor can be converted into Norton's equivalent resistor and vice versa. And how do we do that? If we are given a Thevenin's equivalent resistance, then we can replace it to a Norton resistance. What we do is, we take this resistor 12 ohm R Thevenin and replace it to Rn equal to R Thevenin. And then this voltage source is replaced by the current source, and the value of this current source In is given by V Thevenin divided by R Thevenin. It's as simple. It's that simple. V Thevenin is minus 8, R Thevenin is 12. So we have this is equal to 4 into 2, 8, 4 into 3, minus 2 by 3. Now this is how what we calculated in this one using a totally different procedure. But this and this are equivalent. You don't need to solve if you know one of them. If you know the Norton circuit, you can convert it into the Thevenin circuit. If you know the Thevenin circuit, you can convert into the Norton circuit. In the same way, let us say we did not know about the Thevenin circuit using the way we calculated, and we have already calculated using the Norton circuit, and someone asked me to replace this current source circuit into a voltage source circuit. We can do it very simply. All we have to do is replace this circuit with this circuit. This resistor, if we call it RTH, has the same resistance value as Rn, or equal to 12 ohm. And this voltage will have the value VTH is equal to I Norton multiplied by R Norton. I Norton we had calculated minus 2 by 3, R Norton was 12. 3 into 4 is 12, and 4 into 2 is minus 8. So we replace this thing such that VTH Thevenin circuit is equal to minus 8 volt. So no matter whether you start with if you start with the Norton theorem, you can convert it into the Thevenin's circuit later on. If you start with the Thevenin circuit, you can convert into the Norton circuit. In electrical circuit, in many times there are electronic devices or circuits that are current sources, and if that current source is given, we can convert it into the voltage source, or voltage source is given, we can convert it into the vice versa in the same way. If you want, we can do some more problem. Maybe I will try to give you some problems that you can solve it for your exercise. Make sure you check the links below. Let us solve another problem. We had done this problem in the Norton circuit, but we will do it using the in the Thevenin circuit, and then we will use it using the Norton's theorem. We are given this circuit, and we need to find out the current in this load resistor RL for different values of the load resistor. And before doing this problem, we will find a equivalent Norton circuit. So this is point A and this is point B. So let's first find out the Norton resistor. We are going to replace this whole circuit using a current source and a resistor, call it IN, I Norton and R Norton. We need to first find out R Norton. How do we do that? We replace all the voltage source using a short circuit, and this is 6K. Voltage is replaced by this short circuit. We have a 3K resistor, and we have removed our load resistor from the picture, but retained the points on which this load resistor is connected, and we have connected a multimeter here, and we are trying to measure what is the resistance here. This is what is our Norton resistor. We also call it as Thevenin's resistor. This 6K, if you rotate it and bring this point and connect it here, these two resistors are in fact in parallel, and their equivalent resistance will be 6 multiplied by 3 divided by 6 plus 3, call it R equivalent, the resistance of two parallel resistors. 18 divided by 9 is equal to 2 ohm. So we have found Rn equal to 2 ohms. The next thing we need to find out is the current source, the value of that current source. How do we do that? If you want, you can pause and try it. and check back the solution. So what we do is we short this RL circuit. How does the circuit look like once I short it? This is 6K. And we have shorted this and we are trying to measure the current in this one. This is 3K. What happens if I short this and this? Any current that comes and tries to flow, all the current flows through this resistor, this short current. No current flows through this one. That means this resistor of 3K is effectively, we can remove this, and we are trying to find out the current flowing through this. And what that current is going to be? This current is going to be simply this 36 volt divided by 6K. 36 volt divided by 6K, or 6 milliampere. What we have in the Norton's equivalent current is 6 milliampere in parallel with a 2 ohm resistor, and there we need to find out what if we are connecting a load in between this point and this point. If this is a short circuit, RL equal to 0, what will be the current in that case? Just think about it. What if I short this thing? All the current coming from here, usually the current will divide in this circuit and this circuit depending upon the ratio of the resistors. The one that has a lower resistor will have a higher current. The one that has a high resistance will have low current. In this case, this is short circuit. So the current will find the path of the lowest resistance, which is 0. So all the current will flow through this. So in this case, the current will be equal to 6 milliampere. All of this 6 milliampere current will flow. The second part, let us change it to 1 ohm. 1K, this is 2K. Okay, Rn was 2K, I'm sorry. And this is 1K. If this is 1K, the current will be redistributed such that more of it will flow through 1K and less of it will flow into 2K in the ratio reverse to that resistor values. So the current in this one will be given by the other resistor 2 divided by 2 plus 1 multiplied by 6 milliampere. This will be 3 to 2, 4 milliampere. 4 milliampere current will flow into this. If you have trouble visualizing this, you can also apply Kirchhoff voltage law. Let us say I current flows in this one. Then 6 milliampere current flow starts. I current goes this to this. The rest of this will be 6 minus I. This much of milliampere. Let us say I is in milliampere. Now voltage across this is same as voltage across this. Voltage across this is I into R. 6 minus I multiplied by Rn, which is 2K, will be equal to I into R. I into 1. This is I into 1K. 2I plus 1I is 3I is equal to 6 into 2, 12. So I will be equal to 4 milliampere. So you can use it as a quick method, or you can apply Kirchhoff voltage law. In the same way, you can keep finding the next one. Let's say 2K. Let me do it real quick. You can easily say that if it is 2K, and this is also 2K, this one is also 2K. So the 6 milliampere current starts and is divided half into each of these. 3 milliampere here, 3 milliampere here. Or if it is 4K, if this resistor is 4K, less than half of the current will flow in the higher resistor and more in this resistor. So how do we find the current in the 4K? That will be 2K divided by 2K plus 4K multiplied by 6 milliampere. 6 multiplied by 2 by 6 or 2 milliampere. In this one, if this is 4K, the current will be 2 milliampere. So that's how we can find out for different load resistors the values of the currents. That was another problem. We can go on doing more problems if you want. That helps you solve your problems in exam or strengthens your understanding. One more thing you need to understand is the superposition theorem, and I have not prepared that lecture yet, but I will try to do that. I would like you to try this problem. We have done it in Thevenin's theorem, but now I want you to try it using the Norton's theorem. This is a 12 volt. This 12 volt battery, it looks like a Wheatstone bridge, but it's not a balanced Wheatstone bridge. This is our load resistor RL, and we need to find the current flowing in this one, but this time you need to use the Norton's theorem to find the current into it. So coming back to the Wheatstone bridge, let us mentally remove this RL resistor from this picture. We have two loops, one this one, another this one. So this voltage of 12 volt gets divided half, so it becomes point A is at 6 volt with respect to this. When you take this loop, the voltage at point B will be smaller because this is smaller resistor, this higher resistor, it will be slightly less than 6 volt. So A point will be higher and B point will be lower. The bridge is not balanced. There will be flow of current in this RL resistor. You need to find that out. I have this earlier answer. VTH, Thevenin's resistor, is 2 volt and RTH is equal to 4.5K. I will do the conversion thing and you need to do through the actual process. That means this whole circuit could be replaced by, I solved it in the Thevenin's lecture, 2 volt, this is 4.5K, and this is our Thevenin's, this is RL, connected between the points A and B. I can convert this Thevenin's circuit into Norton's circuit that will have a current of I given by V Thevenin divided by R Thevenin. V is 2 volt, R is 9 by 2. So this is going to be 4 by 9 ampere. 4 by 9 milliamp. This is 4 by 9 milliamp. And this resistor will have the same value as RTH or 4.5K. This is 4.5K. And then you can go on to connect your R load. What I require you to find is, if you do and solve this problem, you should end up this kind of circuit, a Norton circuit, and that's what is required in this problem. Hopefully it should be a good exercise for you. This is where I am. If you have any comment, write it in the comment section, and I will have some link in the comment section where you'll have more exercise and a text on a website where you can read this study material.